Exciting digital design class. In our last exciting digital design class, we were doing homework number 3. Did anybody have any questions about homework 3? Well, seeing none, then I think what we'll do is we'll move on to homework number 4. Unless you guys have questions. So what I'll do is let's take a look at what is called a two-variable kmap, which is right over in here. Two-variable kmap is an interesting construct, and it is discussed from pages 55 to pages 65 in your book. And in fact, that's assigned reading. Hopefully you guys have been reading along, but if not, try and make an effort and see if you can do some reading. So basic idea is this. If you have A, B, or A prime B, that must be equal to B times A or A prime. A or A prime can be simplified to 1, and so that must be equal to B. So what we can do when we arrange our truth table in the following manner, 0, 1, 2, 3 are the elements in the truth table, base 10, is we can see the binary correspondences. And what we do when we loop, for example, from here to here, we're looping A, B prime, and A, B. And what we're doing is we're canceling out B or B prime by factoring out A. So this looping is a graphic correspondence to a Boolean algebraic simplification. And that Boolean algebraic simplification enables me to quickly come up with a minimal form. Similarly, when we see the loops over in here, we again see A prime and A being factored out from B. A prime or A is equal to 1, and so this loop corresponds to B, whereas that loop corresponds to A. And the one thing we can say as a general heuristic is that B is changing in this loop, but A is not. And so A survives and B gets annihilated. Here, going in this direction, we see A is changing, B is not, so B survives and A gets annihilated. And so when you're looping, what you're seeking to do is find simplifications. And in the process of finding those simplifications, you come up with what's known as a minimal sum of products, or, as we say in the biz, MSOP. Notice the terms of the field now include the canonical sum of products, the canonical product of sums, and now we have a minimal sum of products. Minimal forms are almost never, well, are generally not canonical forms, and canonical forms are generally not minimal forms. Moreover, canonical forms are unique. Minimal forms are not unique. There could be multiple minimal forms that will give you a minimal answer. But when you get to canonical forms, the forms are always going to be the same. The order of the product terms might be different in a canonical sum of products, but the number of product terms and their disposition will not change.
So if you were to simplify a minimal sum of products to a single definition term, what would it be?
A minimal sum of products consists of a equation that is not reducible any further. I would say optimal in size, or minimal, if you like, minimal in size. So what you're trying to do when you come up with a minimal sum of products is get the corresponding circuit to be smaller. So let's think about this a minute. If you were to write this out in canonical sum of products, you might see something like this. That is a perfectly fine equation. That is a canonical sum of products. I can write this out. So this is not a minimal form. It is a correct expression for F. And there's nothing wrong with it. It's just not minimal. Now let's try and come up with the minimal form. F equals A or B. First of all, you can see the equation is smaller, but even more importantly, look at the difference in the size of the circuit. It's one OR gate. It's faster because you have 2 gate delays here. It's cheaper because you have 4 gates and here you have 1. It gives you the same exact answer because it's a minimal form. So at some level, one could make a compelling argument that a minimal form will give you a minimum cost circuit. And so you could define it in this way. Moving from a canonical form to a minimal form minimizes the cost of the circuit, but it also minimizes the execution time and it minimizes the amount of space. So it's a win-win-win, right? It minimizes cost, minimizes space, minimizes number of gates, minimizes connections, minimizes complexity, and minimizes delay, or you could say maximizes speed. So lots of benefits to finding a minimal sum of products. In fact, if you think about it, if these gates were made with something like tubes or relays or worse, qubits, which are totally expensive, then you would have an enormous cost compared with a simple cost. Your biggest quantum computer today only has 100 qubits. You really have to be careful how you use those qubits. Maybe in 2 years, IBM will have a milestone quantum computer with 1,000 qubits. If you're wasting your qubits, you're wasting big money because those qubits are hard to come by. And maybe in 10 years, you could have 1,000,000 qubits. Imagine trying to program a computer with only 1,000,000 bits. I mean, I get a Raspberry Pi called a Pi 4. It's 8 gigabits. And what am I supposed to do with 1,000,000 bits? That's not even bytes, just 1,000,000 bits. My Arduino does more than that. So by a lot. So this is I'll say this is the dawn of the quantum computing age, if that. Let's try another example. Let's do a 3-variable kmap. Here's one already made up, ready to roll. So here's a 3-variable kmap. That's a good one. Now let's take a look at how this is numbered. 0, 0, 0, 1, 1, 1, 1, 0. What's the difference? Well, let's see. 0, 0 to 0, 1. There's only one bit of difference. From 1, 0 to 1, 1, there's only one bit of difference. From 1, 1 to 1, 0, there's only one bit of difference. Why? Why is that? Well, because when I go from 0, 0 to 1, 0, it's like right, and I do a loop, right? It's like looping A prime, B prime with A, B prime. If I factor out B prime, the A prime or A disappears, and that gives me just B prime. Similarly, when I have only one bit of difference, I can instantly do my factoring. So here's a case where we're going around the corner. So this is kind of interesting because this represents a wrapping. These two elements are adjacent. And as I go from A prime, B prime to A, B, I can see how, A, B prime, as I go from A prime, B prime, or A, B prime, I can see how B prime can be factored out. And I can get a simplification. What about C? C is over in here. C is not changing. So when I look at this loop, I see B prime, which is unchanged as a 0, and I see C prime, which is also unchanged as a 0. When I look at that loop over here, what do I see? Well, A and B are both unchanged. So I write A prime because A is 0, B because B is a 1. Then I write C because C is a 1 and also unchanged. The smaller the loop, the more variables in the product term. The larger the loop, the fewer variables in the product term. Loops can be an integral power of 2. What does this mean? It can be 2 to the 0, which equals 1. That's here. It can be 2 to the 2, which is equal to 2. 2 to the 1, which is equal to 2, which is here. It can be 2 to the 2, which is equal to 4 different elements. And I don't have a good example of that. But one thing you can do is you can see that over in here. 2 to the 2 is 4. I can have 8 elements at a time. I could have 16 elements at a time. I would expect this in a 4-variable kmap, this in a 3-variable kmap, perhaps in a 2-variable kmap. I don't think you'd want a 1-variable kmap. There's no 1-variable kmaps that I'm aware of. Let's do another. Yeah, this is a good one. I like this one here. This comes from one of the problems in the homework. This, by the way, is homework 7. I'm sorry, problem 7, homework 4. This is problem 6, homework 4. And if you look at it, you see what you've got is a 4-variable kmap. 4-variable kmap. I'm looping this guy all by itself. Looping 12. What's the product term going to correspond to? That's the product term for 12. Habibul. Haven't called on you lately. Habibul, what do you think?
I'm not sure.
Well, let's think about it. A and B are unchanged. C and D are unchanged.
Yep.
So as a result, A, B, and C and D are all going to appear as variables in the product term. Now the question for you is, which ones are inverted?
Will they all stay the same?
Well, the C and the D are zeros. So these are the ones that are inverted. And the A and the B is not inverted because these are ones.
Oh, okay, I see it.
Let's do it again. You help me. Here comes a loop and it involves 5 and 7. Okay. What would this product term be, do you think?
Well, we see that there's 2 zeros at the left side, so C and D would be inverted.
Okay, so here's C and D, and it looks like C is changing. So that's removed. D is maintained as a 1, so it's in its uninverted form. It looks like A and B are unchanging, so they both survive. But what sign do you think A should be?
Inverted?
Yes, because there's a 0 where A corresponds, A, B. So let's do it again. You do this one here for me. 6 and 7 are looped. What shall we use to represent the product term for the loop on 6 and 7?
The 1, 1, and the 1, 0. So we're gonna,
Can you give me the letters? I'm going to write A, B, and what do you think about whether D appears?
so we wouldn't have D, we would have C.
Correct. And what should the sign be for A?
Because it's one, it would be inverted for A.
Correct. That is correct. Now you do this next one by yourself, and you tell me what that should be. We're looping 3 and 7 now. What's changing? Is A changing? The
No,
answer-
A
no,
stays the same.
doesn't change. And is it prime or unprimed?
Unprimed.
It's
Like
primed because it's 0.
right.
What about C and D? Are they changing?
No,
So should I write them here? And what would they be, primed or unprimed?
unprimed.
Unprimed is exactly right. That's exactly right. Okay. Now, who's confused? Anybody? No?
I'm a little confused, Professor.
Yeah, I'm a
You
little
got
confused
a little
too.
confused. Okay,
Yeah.
that's all right.
Me too.
That's all right. It's all right. It's all right. Let's do another one. I'm gonna go through here.
So for that one, Professor, it was a total of 3 loops in that one?
Yes.
Okay.
Well, wait a minute. No. I think there were 4, weren't there? That loop. 2, 3, 4. How many is this? 1, 2, 3, 4.
Oh, okay.
Right. So in other words, I could loop 6 by itself, but I would not get a minimal form because that would have 4 variables in it instead of 3. So if I loop just 1 in a 4 variable kmap, I'll have 4 variables in a product term. If I loop 2, I'll have 3 variables. If I loop 4, I'll have 2 variables. If I loop 8, in other words, an entire side, for example, then I would have only 1 variable. And if I loop the whole thing, it would be a constant. And I'd have no variables, I guess. Let's do another one. So here is here's a loop over in here. And you can see the 4 variables, A, B, C, and D. They're all corresponding to 0. And there's 4 variables in that loop. So that's good. Now I'm going to increase the loop size to 2. So we'd expect 3 variables to be in the loop. What do you suppose they would be? Daniel Riesman, haven't called on you in a little bit, or maybe even yet this semester. So it's your turn. How shall we describe the loop for 6 and 7?
Kind of unsure because I'm still kind of confused with this whole like looping. So would it just be, since so it would be A prime, would it be A prime B, right? And then it would just be then C, or wait.
That's correct. The D changes. It looks like, Matteo, you've raised your hand. What can I do for you?
Oh yeah, I was just gonna answer it, but then
Oh, okay. I can call on you next.
alright.
So
Sorry,
here's the
Professor.
answer.
Why don't we show the D?
Because if you look at these 2 terms right in through here, that corresponds to C, D, or C, D prime. And if you want to factor out the common, you get D or D prime. And we know D or D prime is equal to 1. So if something is changing during the loop, we know it gets eliminated from the Boolean algebraic manipulation.
Okay.
In fact, if you wanted to, you could write out the midterms M7 or M6, which correspond to this loop. Those terms have binary representations. And because it's 4 variable kmap, they have leading zeros. And now if you write these things out, you write out A, B, C, D with A inverted, or A, B, C, D with D and A inverted. And now you can take out the common terms, right? And so one thing you can do to take out the common terms is factor out the D. And so now you have A prime B C times D or D prime, which is equal to 1. And that leaves you with A prime B C, which is what we wrote over here. So what we're doing is a graphic manipulation that corresponds to a Boolean algebraic manipulation. And in the process of growing the loop, we are doing more cancellation through the law of absorption. And that cancellation, you might say it's the uniting theorem, is enabling us to do a Boolean algebraic simplification that gives us a minimal sum of products. Let's take a look at this, this center loop in here. Now we're looping 4 elements at a time. 15, 13, 7, and 15. Sorry, 5, 13, 7, and 15. Said it wrong. So now we take a look at it and we say, B is constant, but A is changing, so it gets factored out. So B appears in the product term. Also, when we look on this left side, we see C is changing, but D is constant. So D appears in the product term. And since D corresponds to a 1 and B corresponds to a 1, we leave it in its uninverted form. If it corresponded to a 0, that would be different. Who's still confused?
Can I just ask a question?
Sure.
Can any of these numbers be looped? Like, or are you just picking like random groups of numbers, or is it like specific?
We're trying to get coverage of members of the onset. So we're looping ones.
Okay.
We're not looping zeros.
Okay.
If we were to loop the zeros, we would find a minimal sum of products for F prime. But what we're trying to do is we're trying to find a minimal sum of products for F, not F prime. What that tells me is we're looping the ones.
Okay. Thank you.
Let's do one with 3 variables right up in here. So now it looks to me like I'm looping these 2 ones and those 2 ones. There's overlap here, but that's okay because overlap doesn't prevent the answer from being correct, and it gives me a simplified form. Why? Because if I had 2 loops, well, let's say 3 loops, I would have 3 different product terms with 3 variables each. But now that I have only 2 loops, I only need 2 product terms with 2 variables each. And that is a simpler form. So we see looping in this direction, A is going to be 0, so we got A prime. B is going to be equal to 1, so we got B. C is changing, so it gets canceled out. Looping in this direction, we see C is going to be a 1. Right? C is uninverted. We also see A is changing, so it's eliminated, but B is not changing, so it's a 1. That is uninverted. So that gives us a, this is, by the way, this is question 2 in homework 4. F equals, and we can write A prime B or BC. So that gave us a minimal sum of products. This is minimal. Now, had I written it in canonical sum of products form, I would write M, I'd write sigma M, shorthand notation indices 2, 3, 7. And that's also equal to F. Well, it's off the screen. But it's not a minimal form. But it is a canonical sum of products in shorthand notation. How's that grab you?
Professor, I have a question.
Sure.
Not for like the values 0 and 1, but what determines like the numbers, like numbering like the boxes like 0, 1, 2, 3, 4, 5, like 6, 7, like 7. Is that just
That's the binary.
that?
So if you take this and you write it 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I don't normally number it in binary because I find it a little cumbersome, much easier for me to number it in decimal.
Okay, that makes sense. Thank you.
Sure. And you could do it over here too. For example, here's 13, right? So you'd write 1, 1, 0, 1. So 1, 1, 0, 0 is 12. 1, 1, 0, 1 is one more than that, which is 13. So the binary will correspond directly to these decimal numbers. But if you want to make it so that you are, I don't know, writing it efficiently, you number it in base 10. And you get used to counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's more than one way to draw the kmaps, but I'm going to do it so it's consistent with the book because it's too confusing if you don't. So if you do it this way and you do it and follow the book, other books will be different. That's fair warning, but we're going to try and be consistent in this class. Also, the graph paper is not an accident. Neatness, even though I know my handwriting is a little sloppy, neatness counts. And so if you can keep your work neat when you're doing it, it's going to help you. Believe it or not, taking the time to try and use graph paper and be neat with these sorts of things actually pays off. It's very helpful. to have like lines like this for your truth tables, lines that help you keep your, you know, your kmap straight. And then there are certain, I will call it hygienically good practices, right? Best practice, number your kmaps, number your truth tables, because when you fill out truth tables and then fill out kmaps, if you number your truth tables and number your kmaps, you'll be able to make sure that you've caught your errors. It keeps things straight. Believe it or not, it takes more time, it seems, to be organized and to keep things straight, but in the long run, it will save you time. It will save you time. I know that's sort of, it sounds like something your mother might say before you go to bed every day, always brush your teeth, or you're going to wake up one day and you're going to be old and you won't have any teeth, and then you're going to go rah, 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 rah. So always brush your teeth before you go to bed. Okay, this is me, like being your mother. Always number your kmaps. Always number your truth tables. Right? This is the floss your teeth, or you're going to have gums. You're going to go rah, 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 rah. So that's the yeah, my little speech about numbering kmaps. Let's try a couple of problems from homework number 4, which should be available to you now. Let's try. No, I think we've seen a few of these already. Yeah. I'm going to try problem number 4. There.
I've got a question.
Yes.
So I see that you go 0, 0, then 0, 1, 1, 1, and 1, 0 all along the outskirts. Explain this to me as if I don't know anything. How do you determine when you combine these factors together, what you get in the boxes?
Okay, so this truth table, well, I say this kmap came from a truth table. So, well, I filled in this kmap from a truth table, put it that way. So what I did was, you want to know how I numbered across the top, right? Is that what you're asking?
No, I was asking how, I see already how you numbered it, but how do you take those numbers and then subsequently extract what value should be in the boxes when they cross over?
So that's the binary. So for example, if we said 15 corresponds to 1, 1, 1, 1, we could see 1, 1, 1, 1. If you wanted to write 12, right, base 10, that would correspond to 1, 1, 0, 0 in base 2. And here's 12. And look at that. It's 1, 1, 0, 0.
Okay, so for the right-hand side, like one of the numbers on the right-hand side, that's just the resultant of combining everything in binary.
Exactly. Exactly. So these are the least significant 2 bits. These are the most significant 2 bits.
Okay. Oh, so the most significant are brought to the forefront and the least significant are the last 2.
Yep. Yep. So for example, here it's 3. In 4 variables, we write equals, right? So that's 3. And now you can see it's 0, 0. There's 0, 0. 1, 1. And here's 1, 1. So I'm writing in base 10 the binary correspondences that appear on the top and left. Is it making sense?
Yes.
Okay.
So I saw that you marked stuff out with the marker in purple. What is that indicative of?
This is the truth table.
Oh, that's just the truth table on the outside.
Yeah, so if I were to do it this way, number my truth table. Two things you should know. One, I use graph paper because it really helps organize the rows and the columns, as you can see. Second, I number my truth table and I number my kmap. Why? Because now I could say, oh, I want ones, ones on rows 8, 9, 10, 10, and 11. That's easy because I can look up 8, 9, 10, and 11. See how easy that is. Then I look this up. It says 14, 15, or 13, 14, 15. Oh, great. 13, 14, 15. Everything else is 0. So I just fill in the zeros. By numbering the truth table and numbering the kmaps, I just made my job of filling out this truth table 10 times easier, 100 times easier, because I didn't have to sit there and decode this binary and try and do it in my head. And I'm bad at doing that stuff in my head. And if I'm bad at doing it in my head, you guys are going to be awful at doing it in your head. So number your kmaps, number your truth tables, and now you can see how the truth table maps directly into the kmap. So row 12 is a 0. That corresponds to this. Sorry, you got a question?
Yes, I have one question. So the purple that you did, that's given to us, or the purple you wrote?
Yeah, open up homework 4 and go to question 4. And you will find this kmap is printed in homework 4.
Oh, okay, now I understand. Thank you.
Yeah, so this was given. And the question is, let's see. And there's no color, okay, in the blackboard. But the question is, what's this loop called? So I'm doing it in purple. And what product term would you use for that? Let's try Stephen Burns. Stephen, I haven't called on you.
Hello.
before.
Wait. Okay. Can I ask a question after I answer?
Sure.
Okay. So you have A and B, they are not changing.
Yep.
So A and B. Oh, wait, is this the question? Is this the question or no?
Yeah, the question is what is the product term
Okay.
that corresponds to the
Okay.
purple loop?
Okay, so A and B are not changing. And C is not changing and D is changing. So, and they're all 1, so it would be A, B, C, which is not an option.
Okay, so as you go across this loop, you were first correct. A is not changing and B is not changing.
Oh, but
If you
B is
go-
0, so it's not right. So
B is going to be
so it's B is,
prime.
yes, okay.
So B is prime because that's a 0.
Mhm.
A is not prime because it's a 1. And
Mhm.
when you go down, C is changing and D is changing. So they're both eliminated. So because you have looped 4 elements, you get 2 variables. Had you looped only 2 elements, you'd have
Okay.
3 variables.
Yeah, I don't know why I was only looking at the bottom two for some reason, because
It's all
but
right.
my question is, as I'm looking at all of these, like, why is it in the order of 0001 1110, like on the outside of the table?
Yeah. So this is a one bit of difference between 00 and 01, and that bit is the least significant bit.
Mm-hmm.
From here to here, one bit of difference from 01 to 11, and that bit is the most significant bit. From here to here, one bit of difference from 11 to 10, and that bit is the least significant bit. What you have is known as a Hamming distance of 1. That is the number of bits that's different as you go from one thing to the next. Here's the other thing that's kind of cool. Suppose you traverse in the following way. 0, 1, 3, 2, 6, 7, 5, 4, 12, 13, 15, 14, 10, 11, 9, 8.
Do they only vary by 1 bit each time?
Exactly.
Okay.
Exactly. So now I can write 0000, 0001, 0011. Look, only 1 bit changed. 0010, 0110. Only 1 bit changed. 0111, 0101. Only 1 bit changed. 0100, 1100. Only 1 bit changed. 1101, 1111. Only 1 bit changed. Only 1 bit of difference exists as we go from one row to the next. Right? Going from 14 to 10, only 1 bit changes. I think I did that right. Only 1 bit changes. Only 1 bit changes. There's only 1 bit of difference as you go from one row to the other. And what that means is if this is A prime, B prime, C prime, D prime, and that's A prime, B prime, C prime, D, I can factor out these two things, eliminate the D or D prime because they're both equal to 1. So that form of looping comes directly as a simplification. Oh, I'm off the screen, am I? Sorry about that. That form of looping comes directly as a simplification as a result of how the binary has been arranged. And that's why we number in this very peculiar looking fashion. So that when we traverse in this way, we're always traversing from one, from one binary vector to the next with a Hamming distance of equal to 1. Having said that, I could have done it differently. I could have traversed this way and gotten the same result, which is cool.
It's interesting. Thank you.
Yeah. So then the question is, what kind of a wacky genius thought of this? I often think, where did this come from? It's a kmap. It came from Maurice Carnot. Okay, that's great. How did he figure it out? Well, actually, he just borrowed what's called the Vetch map. The Vetch map, what's that? Well, Edward Vetch came up with this in 1952. And in fact, he didn't invent it either. Holy mackerel. So Maurice Carnot did it in 1953. You think, wow, what a genius. He didn't invent it. He borrowed and simplified Edward Vetch's map, known as the Vetch chart from 1952. And Vetch didn't invent it. It came from Alan Marquand. Alan Marquand did this in 1881. So he might have been a contemporary of George Boole. And these guys, I don't know, back in 1881, they must have been smart or something, because they came up with this in the Victorian era before they had anything other than Babbage machines, which were essentially very large mechanical calculating machines. No electronics, no vacuum tubes, no relays, no transistors, no integrated circuits. And they're sitting around coming up with this stuff. Victorian era computing. And it's still good today. And we use it today. So that's cool. Very cool. So that's I actually took the paper from Edward Vetch, and I put it up on under the background section. If you go into the course content, you'll see the paper is uploaded there. And you'll also see Carnot's original paper too. But the one thing I didn't get was the 18, well, what was it? 18 something or other. Marquand diagram, 1881 logic diagram. So I got to go back in time and see if I can find out how to get the paper from 1881. Smart. And they did it without computers. I don't know if you noticed, but aside from the fact that we're using Zoom, I'm kind of teaching this without computers, right? However, having said that, there are computer programs which will help you to do the minimization of forms, including Quartus. And once you get to anything beyond 4 variables, I claim you're really better off using the computer to do the minimization. But for now, we can do it all by hand, and it kind of comes out, I don't know, with relative ease. We don't need no stinking computers for this. Or I should say, we use the best computer of all, the computer between our ears. That's a good computer. I like that computer. So, so there. Let's see now. Where are we on this homework assignment? I think we've done homework. Did we do problem 5? I don't think so. Let's do problem 5. So there's problem 4. Let's take a look at problem 5. So here's problem 5. That's looking pretty good. Right now we're looping the center and we're calling it BD because A is changing, but B is not. B is 1s, so it stays uninverted. And then we take a look at C, it's changing, D is not. And because D is 1s, it's uninverted. So there's your BD. And now we've got another one here. We see A is not changing, so it's a 1, so it's uninverted. B is not changing, and it's a 0, so it is inverted. D, well, D is indeed changing. C is not. So let's not put too fine a point on it, but what I'd like to do is I'd like to say that this term corresponds to M11 plus M10. And M11 corresponds to 110. Sorry, one that doesn't. It's 110 11 or 1010. A, B, C, D, A, B, C, D. Whenever there's a 0, I put in a prime. Here there's a prime. And now you want to see what you can factor out. Check it out. I got A, B prime C, A, B prime C. I can factor out D or D prime. That goes to 1. And that's where I get A prime. I'm sorry, A B prime C. A B prime C comes right in there. So that's why you're able to do that looping. And it's because of how we've done our numbering up here on the top and on the sides. Isn't that interesting? So if we looked at the terms in green, they combine to give us A, B prime, C. And if we look at the term in the upper left, that's A prime, B prime, C prime, D prime. So this is a multiple answer question. You have to choose the 2 answers that are correct. And it happens to be the one that says that this term in the green over here is A, B prime, C. And this term in the green over here is A prime, B prime, C prime, D prime. All right, let's take a moment and ask questions.
So when you're when you're grouping like the ones together, like so first you look like the values for A and B, and then for C and D, and then write down whatever product you have. Just for clarification.
Yeah. What the point of looping is to try and do combinations that will give you simplified product terms. So when I loop all 4 of these elements together, what I can expect is only 2 variables appear in the product term. It's a simplified form. If I looked at the canonical form, there would be as many product terms as there are ones. So there'd be 1, 2, 3, 4, 5, 6, 7 product terms with 4 variables each and OR gates, or at least one OR gate with multiple inputs that would OR all of the product terms together. But now here in a minimal form, instead of 1, 2, 3, 4, 5, 6, 7 product terms, I only have 3 product terms. And they're simpler for product terms, except for this one, which is, well, I couldn't loop it. There were no loops available. Any other questions? Yeah, Alvin, yes.
Is the loop just random? Do you just choose a random spot to loop, or you loop the ones?
You want to loop the ones because you're looking for F. So F equals BD or A B prime C or A B C D all primed. That's what you get when you loop the ones. If you loop the zeros, you'll get F prime. Moreover, you want to make your loops as large as is possible within the permission enabled. So you can't loop like this on a diagonal, and you can't loop 3 elements at once, like these 3. That doesn't work. You got to loop an integral power of 2. You can't loop on diagonals this way.
But you can loop 4 together like that?
You can loop 4, you can loop 8, integral power of 2.
No matter the way you loop it, like it will come out to be the same answer in the end though, right?
Well, no, you may get different answers. For example, over here, the purple is legit. You can loop around the corners and you can loop these 2 purple ones, or you could loop these 3 purple ones, not both. If you loop both, the purple and the green, it won't be minimal, but you can get 2 different possible minimal forms. In other words, minimal forms are not unique. Canonical forms are unique. You get your choices in how to loop, either purple or green, but not both. And if you think about it, the green is going to give you 1, 2, 3 loops. The purple should give you 1, because that's going up, that's 1 loop going back and forth, 2 or 3 loops. So you're going to have 3 loops of 2 no matter which you choose. But you have to choose one, not the, you have to pick one. Now, first time I looked at this, I picked the green. But then somebody pointed out, oh yeah, you can also loop the purple because you can go around the corners. It's permitted. What do you think of that?
It's kind of weird to wrap your head around.
Yes. Yes, it is. It's bizarre. It's bizarre. No doubt. No doubt. Let's try and see if we can come up with a rationale for this type of looping so that it makes some kind of sense to us. What we'll do is we'll draw a square. And then in the square, what we'll do is 0, 1, 1, 1, 1, 1, 1, 0, 1, and 0, 0, 1. So in the square, we have 0, 1, 3, 2. And remember, we're doing things like this, 0, 0, 0, 1, 1, 1, 1, 0. So there's 0, 1, there's 0, 0, here's 0, 0 here, 0, 1 is here, 1, 1, oh, I'm off the screen, shoot. So here's the 0, 0, it's here, 0, 1 is here, 1, 1 is here, 1, 0 is here. Now let's extend it to 3 dimensions. And what we'll do is we'll copy 0, 1, 0, 0, 1, 1, and 1, 0, just from the first 2 bits. And then what we'll do, instead of using 1s in the rear, we'll use 0s in the front. And now what we'll do is we'll draw the kmap. And then what we'll do is we'll say 0, 1, right? 2, 3, 4, 5, 6, 7. And now the question is, why should I be able to loop 0 with 4? Because 0 and 4 are right in the front. Why should I be able to loop 1 and 5? Well, because 1 and 5 are right here in the back. Why should I be able to loop these two together? Well, because that's like looping the whole floor. So this is a 2-dimensional perspective projection of a 3-dimensional object, and this chart captures the relationships in this two-dimensional perspective projection. How's that for a mind bender? And now here's another one. You're going to love this. It's on the front cover piece of your book. And you can do the whole thing in 4 dimensions. And that creates the so-called 4 cube. And the 4 cube can be extended to a 5 cube, but the problem is I can't draw it. It's hard, and it's not in the book either. But in fact, you can do 5 and 6 variable kmaps, and it gets all kinds of messy, which is why I say use computers when you go beyond 4 variables. So that's the that's the rationale in 3 dimensions anyway for looping with a 3 variable kmap and coming up with, I don't know, I'll say the geometric argument for the looping. Having said that, look at what happens when you loop 0 and 4. You have A, B, C, and A, B, C corresponding prime, 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 and prime, prime. And what have you done? You factored out B prime, C prime with A or A, right? Because there's the A prime and there's the A, and this is equal to 1. So that looping is this algebra. And when you loop all 3 of these things together, well, what happens? You can see it here in the kmap. Sorry for not labeling it. I should have labeled it. A is changing, C is changing, B is not changing. So if I loop 0, 1, 4, and 5, I'll put it in a different color so you guys can see it. So when you loop 0, 1, 4, and 5, you see B. It's a simplification. What do you think of that? It's mind-bending, isn't it? Any questions about this? I know it's a lot to kind of get your head around, but that kind of gives you the bird's eye lowdown on the kmap caper, whatever that means. Any questions? Maybe I should open up my chat and see if people are chatting. So shall we try another question out of homework 4?
Yep.
All right, let's do that. Let's do that. So in this one, how am I doing here? Oops. Now, he says, let's do this in purple. 1, 1, 1, 1, 1, and I want to get a different color. Okay. You tell me. Let's see. Dominic. Haven't called on you in a while. Dominic, what should I loop?
The 5 and 7, 3 and 7, 6 and 7.
Oops. And what about this 12 over here. I haven't got coverage on that. How do I loop that?
Do you just loop it by itself?
Yep, that's exactly right. And so if you're still with me on this, why don't you tell me how to label element 12?
So that would be,
Would it just be A, B, and then C, D with the, I forget what it's called, the
Prime.
prime, C prime and D prime?
Yep, that's exactly right. Want to take a stab at the 6-7 loop?
Yeah. So that would be
A prime B, and then it would be
just C.
Yep. Want to try the 5-7 loop?
So that would be A prime B again, A prime B again. And then it would be just D.
Yep. And why don't you finish this off?
This would be A prime, C and D. Oh, wait, sorry. Yeah, C and D.
Yeah, you got it. And that's it.
Yeah.
Thank you. So, who's confused by this? This is problem number 6. I think you guys are getting it. I mean, it sounds to me like you're getting it. We got a little time. We could do another question. No questions about this? Everybody's all right with this?
Just a question for looping. Could you not do, just for clarification, you could not do 5, 7, and 6 altogether as one loop?
No, because integral power of 2 means you can do 2 to the 0, which is 1, 2 to the 1, which is 2. You can't do, well, I'll just say 2 to the 0 is equal to 1, 2 to the 1 is equal to 2, 2 to the 2 is equal to 4, 2 to the 3 is equal to 8, 2 to the 4 is equal to 16, right? You don't see 3 in here anywhere. You can loop integral powers of 2. And I should say positive. Well, not necessarily positive because 0 is not positive.
So like if
Non-negative integral powers of 2. How's that?
so like if the fourth element was like a 1, you could do 4, 5, 7, and 6. Like,
Oh, sure. Yeah, you could loop this whole thing, and then if you loop the whole thing, it would be A prime B, and you wouldn't need any of these other product terms because you'd have coverage over 4, 5, 6, and 7.
Thank you. Okay, thank you.
Sure. Yeah, it's a good question. Good question. Let's try. Oh, and the answer. 6 says, how many loops do you need? I got 1, 2, 3, 4. So that's the answer in question 6. That's how many loops you need. But this is better because I've shown you how to get the minimal sum of products. Let's do. I gotta say, I know some people preferred the iPad, but I gotta say, I really like graph paper. It really helps out when it comes time to, making things just a little bit neater. Let's do a 3-variable kmap from question 7. So this will be question 7. And then I think we're going to have to call it quits because I got another meeting coming up after this. 0, 1, 2, 3, 4, 5, 6, 7. And according to question 7, I got a 1 and a 1 and a 1. with zeros. And then the question is, Ashley, I haven't called on you in a while. Ashley, what should I loop?
To be honest, I'm still very lost in this situation.
Oh, okay. Well, I'm trying to loop the ones, and I'm trying to make the loops as big as possible. So
Well, there is the quadrant in the top left, the quadrant in the top right, and the quadrant in the second row, third, or sorry,
could just
yes,
say
2 by 2,
element 3.
element 3.
Yeah, and that's great. And so we need exactly 2 loops to get a minimal form. And can you, Ashley, tell me, please, what would you call the loop on 0 and 4?
I forgot the exact name, but it runs past, like it goes from one side to the other, and it's still one continuous loop.
Let's identify the product term in terms of A, B, and C. Will A appear in the product term?
It should, yeah.
See, now A is changing though, right? So the A is eliminated. So if we look at 0 as M0 and then M4, what we see is 0, 0, 0 and 1, 0, 0, which corresponds to ABC, ABC, and then the primes are where the zeros are, you see? And so what you do is you look at the BC prime times A or A prime, because you're factoring out the common terms. This goes to 1. And so at the end of the day, when you see that A is changing, you're factoring this out automatically. And so what you get left is B prime and C prime, because B is unchanged at 0 and C is unchanged at 0. And there it is, B prime, C prime. So that's the product term.
Okay.
Ashley, why don't you tell me what the product term is for element 3, and then we're going to call it quits for the day.
For element 3, nothing changes, and so it is A prime, B, and then C. Yeah.
Correct. That is correct. So I think we're getting it. Please read pages 55 to 65 on kmaps, and we'll continue this on Monday. Thanks very much for your time. Enjoy the day. It looks cold, but clear and bright. Stay safe. Thank you.
Thank you.
Thank you, Professor. Have a great weekend.
You too. Thank you.
Thanks, Professor.
Thank you.
Nice weekend, Professor.
You too.
Thank you.
Thank you.